Okay. So the topic is enthalpy of atomization. This time I'm not going to ask you because it's already 3 times. I'm going to repeat the definition. So enthalpy of atomization means that we are converting the element into its gaseous atoms. Okay. And it has to be 1 mole of any element. Let's say you have sodium. It was in the solid state. That's the standard state. And we use energy to convert it into its gaseous atom. So the symbol would stay same, but we just have to like write G here. G represents the gas. Okay. And let's say that if you have oxygen, a diatomic molecule, so it will convert into single O. So to balance it out, we will write 1/2. And here it will be gas. It was already a gas. Okay, but it was a gaseous molecule. We converted into a gaseous atom. When we write down the delta H, it will be delta H atomization. And we are using energy. So it means it will always be a endothermic process. It can be any value, but it will stay in the positive. Okay, with the same units, kilojoules per mole. Okay. Then we have a definition that is similar to enthalpy of atomization, but the name would be different. Like the concept is same. It is enthalpy of sublimation. Do you know the process of sublimation?
Is it solid to gas?
Yeah,
I
it's
mean,
solid to gas. Yeah, it is
yeah.
exactly same. Okay, so we can write down the same equation here that the solid sodium is converting into gaseous atom. Okay, so enthalpy of sublimation.
Okay.
Then we have and the values would be exactly same. Let's say that if for sodium we have 148 kilojoules of energy in the positive, same value would be for enthalpy of sublimation. Then the next one is bond dissociation enthalpy, or in short, we can name it as a bond energy. I think you must be familiar with this concept. So bond energy means that the amount of energy that is needed to convert 1 mole of a covalent bond or into its gaseous atoms. Okay. Or maybe free radicals. Let's say that you have chlorine. You want to convert it into 2 chlorine atoms by breaking this chlorine single bond. Okay, this is your 1 covalent bond. And when you do this, you create 2 chlorine atoms. Okay, but the one thing is both your reactant side and your product side should be in your gaseous state. Okay, so gas. And right now we are talking about enthalpy of like dissociation energy, means breaking off a bond. So your delta H would be positive because you need energy to break the bond. Then let's say you have a methane molecule and you break down only 1 carbon-hydrogen bond. So it converts into CH3 plus H. Okay. Gas gives you any value in positive. It was already in the gas form. And another thing that it's not necessary that we are always have to create the gaseous atoms. Okay, we can also create radicals. If you remember in AS level, we have done a reaction of free radical substitution. There, if we were like breaking up this covalent bond, our product was chlorine radical, right? So this one will also be considered as a bond dissociation energy. Okay.
Okay.
Clear?
Yep.
Okay. There's one more thing that sometimes now if we're gonna write down this thing, let's Cl2 converts into a 2 chlorine gaseous atoms, right? This is our enthalpy of dissociation. Okay. But this dissociation enthalpy, let's say that this is 100. Okay. 100 when we are creating 2 atoms of chlorine. Okay. But in basic form, we can say that we were breaking 1 chlorine single bond. Okay, so we were needing 100 kilojoules of the energy. It is similar to enthalpy of atomization, but in atomization we had only 1 chlorine, 1/2, and it was creating only 1 chlorine atom at a time. Okay, according to the definition. So this time the energy would be, for enthalpy of atomization, it will be 50 kilojoules of per mole. Okay. So in short, we can say that enthalpy of dissociation is double of enthalpy of atomization. You can see the clear difference. In dissociation, we are creating two chlorine gaseous atoms by breaking one covalent bond. But in atomization, we were doing the same thing, like we were breaking down the bonds. But here, the main point was that we always had to create one chlorine atom or one atom at a time. Okay. So 100 and it will be half to 50 in the atomization concept. Did you get it?
Yeah.
Okay. So sometimes when we are going to like solve this different questions, like mathematical questions, they can give you these two things. Either they can give you the dissociation energy, but if you want to use the atomization, keep in mind that you have to half it to get the atomization energy. Okay. Then the other definitions are same as we have done in the AS level, the first ionization energy and the second ionization energy. So I'm not going to repeat them again. You are familiar with them, right?
Yeah.
Okay. Then we have the new concept here that's about first electron affinity. Ever heard of the concept electron affinity?
Ability to attract.
The
Electrons.
ability. Yep, it's the same. Like the ability of an atom to gain an electron, okay, when it was in the gaseous state, and to produce a gaseous ion. So the exact definition would be the first electron affinity is the enthalpy change that occurs when 1 mole of gaseous atoms gain 1 mole of electrons to form 1 mole of gaseous ions with 1 negative charge. Okay. So it will be oxygen plus electron gives you O negative. It is in the gaseous form. This one is also in the gaseous form. First electron affinity would be negative. Okay. This is delta H. I will give you the reason why. So electron affinity, it's in the negative. The reason why it's in negative, the point is that you have a gaseous atom that is kind of like neutral, okay, and you have an electron. The nucleus of this atom will gain this electron, right? It is kind of like making a bond, I would say, or it is kind of like making a attractive force for that electron, okay. And whenever you make a bond, what happens? That the energy will always be released, okay, during bond formation process. So you can think of the same concept, that there is a kind of attractive force between the atom and the electron, and the electron is being attracted towards the nucleus of that atom, so it is releasing the energy, okay, and that energy would be shown as this form, electron affinity. Okay.
Yeah.
Then the second thing is that whatever ion, or I can like explain it in another terms, that we are making this ion, O negative ion, right? This ion is always more stable than the atom. Okay. And if it is more stable, so let's say that atom is here in the energy graph somewhere. Okay. And ion is here. The atom has 500 kilojoule of energy. Okay. When it converts into an ion, it wants to get rid of that extra energy, and the ion is 250 kilojoule of energy. So that remaining 250 will be released into the surrounding, and that would be shown as a delta H negative. Okay. Why the ion will be more stable? Because of the same concept that all the atoms that you have in the periodic table, they wants to complete their octet, right? So if any oxygen atom tries to gain electrons, it means it is moving towards more stability by having the 8 electrons. Okay. So this thing.
Okay.
Okay, then the next concept is second electron affinity. When the negative ion gains another electron to convert itself into an ion, but with a 2 negative charge. So now here, the value would be positive. Can you guess any reason that why it should be a positive, not a negative one, even though that the same concept is happening?
Uh, because it. Actually,
No guess? Okay. It is basically your answer is in this equation. So what happens? You have an ion that already has a negative charge, right? And the thing that it wants to gain, it is also having a negative charge on it, like the electron, right? So two negatives
Yeah.
cannot come near each other, right? We need to put some force so that we can bring those two negative charges near each other. Otherwise, they are going to repel each other. Okay, so the electron has to overcome the forces. The electron has to overcome the negative forces that are already present on the ion to enter into its last shell. Okay, and to do that, we have to put force or we have to put energy from outside, and that energy is being given as a delta H in the positive sense. Did you get it?
Yeah.
In the question paper, there is a particular question regarding this thing, that why first electron affinity is negative but the second one is positive, or the next, third, fourth, they are also would be in positive. Okay, so the reason would stay same, that in the first electron affinity we were just adding the electron in a neutral atom, so there was no like external force that we needed. But in the second one, we need some external force or energy to put those two negative things together. Okay, clear?
Yeah.
Or the
Yeah.
keyword would be to overcome the repulsive forces that is present between the negative ion and the negative electron. These are the keywords. Got it?
Yeah.
Then now we have a new concept again. The next is enthalpy of lattice formation. So lattice means that your ions, positive and negatives, are coming together. They are having some kind of attractive forces between them and they are making a lattice, a ionic compound. Okay, so the definition is lattice energy of formation. The enthalpy change when 1 mole of a ionic crystal lattice is formed from its constituent ions in the gaseous form. Okay, it's similar to enthalpy of formation, but here instead of having the elements on the reactant side, we will be having the ions like sodium ion and the chloride ion, both in the gaseous form, and we will be making sodium chloride in the standard form, solid. Okay. The delta H of lattice energy will be negative. Keep in mind, enthalpy of formation would always be in negative. Reason, because you are making a force or a bond between the negative and the positive ions. Bond formation process is always negative. Okay, we can have some other examples. Let's say you have barium with 2 positive, you have fluoride with negative. There would be 2 fluorides to make barium fluoride, BaF2. Same gaseous and solid. The product has to be only 1 mole. Okay, that's the definition. Clear?
Yeah.
The other thing is enthalpy of lattice dissociation. Same concept, but in the opposite sense. Like here, we are going to break down the ionic lattice into its constituent ions. Okay, and again in the gaseous form. So, same equation, but in the reverse direction. We are making sodium ion, chloride ions, gaseous, solid. And this time the enthalpy of dissociation, the lattice energy of dissociation would be positive. Let's say that if here it was 500 kilojoule of energy that was released, so 500 kilojoule of energy will be needed because it's the same thing but happening in the opposite direction. So signs will be reversed. Okay, is that clear?
Yep. Yeah.
Any doubts or any confusion?
No.
Then we have the next thing, that's about the trends in the lattice enthalpies. Okay, like in the groups or in the periods. But before discussing that thing, we have to focus that what are the main things that decides that whether the lattice enthalpy will increase or decrease in a group or a period. Okay. So that is the factors that affects lattice energy. The first one is ionic size or size of the ions. The second is charges on the ion. Okay, so if we have a small ion, it means that let's say your sodium ion. Let's compare sodium with a potassium ion. Sodium has smaller size, potassium has a bigger size, and both of them are making a bond with the chloride ion. What do you think? Which one would have more forces of attraction? Sodium chloride or potassium?
Sodium chloride.
Sodium chloride. Can you give me a reason for that?
Because they're smaller, so stronger. It's easier to. Wait, do you mean like between the ions?
Between sodium and the chloride ions. Or potassium and the chloride ion.
Well, actually, potassium then probably.
What?
Because it's it'll have a larger pull on chlorine, won't it? Like
Which one? The
chlorine will be
sodium,
more
no?
attractive. Huh?
The sodium, right?
Potassium.
Like, think about your answer again one more time.
Aren't they gonna have the same force of attraction, like sodium chloride and potassium chloride?
Look, if your ion is smaller now, so it means its nucleus can attract the negative ion more strongly towards itself. Here, the nuclear charge is not going to play any role. Okay, not the nuclear charges. Nuclear charges means the sodium has 11 plus charge, potassium has 19 plus. In the attractive forces between the oppositely charged ions, the ionic charge and the ionic size plays the main role. Both positive ions are having one positive charges on the ion, right? Sodium and the potassium. So it means the ionic charge is same. Then we have to move towards the size. Ionic size, sodium, the one that is smaller. So it means the nucleus is more closer to the chloride ion. Okay, this nucleus can have like more stronger attraction for the chloride, while the potassium has too many inner shells, at least like 3 inner shells, right? So whatever the electrons are present, the inner shell electrons, they are going to have the shielding effect, right? So most of the nuclear attractive force will be used to it will be used by those inner shell electrons. So only less force would be reaching towards the chloride ion, so less attractive force. Okay, I will say it again. If your ionic size is small, there would be more attractive force. Okay, the more stronger bond would be formed. And more stronger bond, it means more energy will be released. More energy released. Okay, clear? Yes. And opposite, if there would be bigger size, less attractive force, less energy will be released. So it means we can say for the potassium chloride, the lattice energy of formation would be less exothermic. And here it will be more exothermic. Please write your answers in form of less exo or more exo. Never write that the value would be bigger or less. Okay? Because both the values would stay in the negative numbers, but it can be more or less. So for sodium, it can be, let's say, minus 500. I'm just like using some guess numbers. And the potassium chloride would be around 100. Okay, so more exo.
Okay.
Okay. Acha, then the second thing is the charges on the ion. If I'm gonna compare sodium with magnesium, the same chloride, what do you think? Which one would be more exo?
Uh, Sodium.
Magnesium or sodium?
Sodium.
Sodium. Why?
It's smaller, isn't it? So there's more.
Do they have the same charge? Ionic charge.
No. No.
Then think about in that sense as well. The magnesium has a two positive charge. Keep in mind, when your ions have a bigger ionic charges, so it means that they are going to attract the negative ions more strongly towards themselves. Okay, the two positive more stronger force as compared to one positive. Okay,
But
it
doesn't
will
have
play the
both
same. It
have
will play the
10.
same concept. I would suggest, kind of like in the size way as well. If you remember that sodium has a bigger size. Okay, even though that they have the same number of shells, two shells. Okay, but magnesium has 12 positive. Sodium has 11 positive nuclear charge, right? 12 protons are attracting those 10 electrons more strongly, right? I'm talking about just the inner electrons, or like the electrons of the magnesium only. Okay, so they are attracting the those 10 electrons more strongly. It means that the size of this magnesium will shrink, right?
Oh, yeah.
It will be smaller. And if it is smaller size and also has two positive ionic charge, it means these two things are going to play a major role, and they will be attracting the chloride ions more strongly as compared to the sodium, where the size is still larger and the charge is 1 plus. Okay,
Okay.
got it?
Yep. Yep.
So now repeat it. What did I tell you about ionic size and ionic charge?
The magnesium lost 2 electrons, but still has uh, 12 protons. So there's a stronger force of attraction, which causes the magnesium ion to be smaller because it pulls the electrons closer. So it's smaller, and that means that the attraction between the positive nucleus and the chlorine atom ion will also be stronger. So
That's right.
yeah.
Acha. Now the questions that will come in exam will be like they are going to give you two or three different kinds of ionic compounds, and they would ask you that which one would be more exothermic or less exothermic, and give the reasons. The reasons should only based on ionic size and the ionic charge factors. Okay, never write about the nuclear charge or the protons or anything else. Just two keywords: ionic size, ionic charge. Okay, let's say that
Okay.
if your answer is sorry, the question is lithium fluoride, and we have beryllium fluoride. Okay, right now I am comparing those two things that belong from the same period, like lithium and the beryllium. Okay, so the answer would be simple, that beryllium fluoride is going to have more exothermic value of lattice formation. Reason, because beryllium ion has two positive ionic charge and it has smaller ionic size. Okay, so more attractive force between beryllium ion and fluoride ion. Okay, listen to the keywords.
Okay.
I talk about ionic charge, ionic size of beryllium, and third, the attractive force, right? And the fourth point would be, of course,
Yep.
that it has the more exothermic value. The next
Okay.
one is if your positive ions belong to different groups and also to different periods. Sodium iodide and calcium iodide. But if we focus on the size, we know sodium would have smaller size as compared to the calcium. Is that right, Michael? The size of sodium, is it smaller or bigger than calcium?
Wait, can you repeat that? Didn't get it. I didn't
Okay,
hear.
I'm asking, which one would have a smaller size, sodium ion or the calcium ion?
Uh, Sodium.
Sodium, right. So it means if we just focus on the size, the sodium should have a more stronger attraction,
Yeah.
right? But here,
Yes.
the main role would be played by the ionic charge. If your sizes are different, and of course the charges are also different, we will always prefer the charges over the size. Okay, that's the rule. If any ion that is even bigger, but still it has like more ionic charge, like 2 positive calcium ion, then the calcium would have more stronger attraction for the iodide ion as compared to the sodium ion. I will write it here. The ionic charge will always have a upper hand over the ionic size. Okay. So in that sense, even though that the calcium has a bigger ionic size, but still the calcium would have more stronger power for the iodide ion. Okay. And as a result, it would have a more exo value. Is that clear?
Okay. Yeah.
I'm gonna give you two compounds and let's see what will be your answer. Mm-mm.
Today is Friday, so do you want to watch topic stories? Yeah, okay.
Okay, sodium bromide and strontium bromide. Which one is having more red flag?
Do I write down an answer?
No, you can just tell me.
لم تفعلوا ف- فزانوا
Hello.
ورسولي وإن
Hello.
More
تبتم
exit.
فلكم رؤوس
Hello.
أموالكم لا تستسلمون ولا تظلمون
Hello.
وإن كان ذو أسرة فنصرة
Hello.
وتقوا
Like
يا
I'm waiting for your answer.
Oh, I was asking, I said, shall I write the answer?
No, I said you don't have to. You can just orally tell me.
Oh, I think the internet. Uh, wait, what is it? Which one has more? Like, which one's more
Negative that
exothermic?
or more stronger attraction.
Uh, is it SN or SR?
This is SR, strontium bromide. Sorry for my writing, but this is one
Okay.
R.
Oh, probably that one then. Oh, wait.
Like any confusion? Laika, can you hear me? I think it's your internet that's having some kind of problem.